So in this video we'll be looking at maybe what might be a rather complicated counting problem, and that problem is counting triangles in our geometric figures. So suppose somebody just walks up to us and gives us a geometric figure, maybe something like this, and the question is simply how many triangles of any size are actually contained in this figure. Well, if we kind of stop for a minute, we can really initially see probably four, having a vertex there at our center point. So we've got one on top, one on the left, one on the bottom, and one on the right. And we can actually see that we've got four more where we have one side of the triangle being along a diagonal of the square. So we can have one on the lower right, one on the upper right, one on the upper left, and one on the lower left. But then the question is, this is just kind of doing this by inspection. Do we have any others? Have we missed any? How do we know that we've actually gotten all of them? And so to really answer this question, what we really need is a systematic way of possibly listing all of the triangles, and that way we can really get an accurate count of how many are going to be there in the figure. And so if we stop and think a little bit, we know that a triangle is going to consist of three vertices. So we might start out by labeling all the vertices of the figure. So we have A, B, C, D, and E for the center point. And then we can say, well, how many three-letter sequences are there can we construct with the letters A, B, C, D, and E? Well, kind of going back to our general counting principle again, we would have 5 choices for the first letter, 4 choices for the second letter, and 3 choices for the third letter. So 5 times 4 times 3 gives us a total of 60 different sequences that we could write down. Now, not every single one of those sequences is really going to give us a triangle. For instance, if we look at just the sequence along one of the diagonals, the AEC, that gives us a straight line, doesn't necessarily give us a triangle. And kind of by that same token, if we do take a triangle, we can really, just looking at this, we can say that there's really a whole lot of different sequences that correspond to the same triangle. That, for instance, ABE, AEB, BEA, BAE, EAB, EBA, those are all going to correspond to the exact same triangle in our figure. And if we wrote those out, we would see that, oh my goodness, there are a total of 60 of them, and we might be wondering at this point, well, is there some kind of better way than this? Well, we'll get to that question in just a second, but kind of continuing with what we've got going on now, if we go through and scratch out all of the sequences that correspond to our lines, such as ACE, AEC, BDE, BED, CAE, CEA, DBE, DEB, EAB, EAC, EBD, ECA, EDB, all of those are going to correspond to these diagonal lines, and so those aren't going to give us a triangle, so we can scratch those out. So really, from our 60 possibilities that we have, we see that we've really got a total of 60 minus 12 of them that we were able to get rid of, giving us a total of 48 possibilities for triangles. Now, for each one of these labelings of a triangle, we've got 6 possible labelings that correspond to the same triangle. For instance, if we take ABC, ACB, BAC, BCA, CAB, and CBA, those are all going to correspond to the exact same triangle, ABC. And so if we want kind of some way that might represent exactly one triangle, one thing that we can do with our labeling is to say, you know what, if we only take alphabetical orderings, then that's only one possible way to talk about one particular triangle. And that can get us a long way. So that's kind of an important observation there. So we'll hold that one back for a second. And if we write down all of the alphabetical orderings that we can have for our vertices, well, there's a whole lot less of those. We can have ABC, ABD, ABE, ACD, ACE, ADE, and so on and so on. And we can see from those, we've really only got 10 possible orderings. And from those 10 possible orderings, 2 of them are going to be the diagonals, ACE and BDE. So if we take those out, then that only gives us 8 possible sequences that are going to correspond to our triangles. And if we go through and check each one of those out, we can see that yes, sure enough, each one of those do correspond to a triangle. And in fact, one of the 8 triangles that we've already found, ABC, ABD, ABE, ACD, so the first 4, ADE, BCD, BCE, and CDE. And so this kind of gives us a way of really thinking about, well, how can we do this now in general? This worked for this one particular geometric shape. Does this work in general? In fact, it does, and this really gives us a strategy for counting all of the triangles in a geometric figure that somebody may hand us. And so our strategy may be something like we want to label all of the vertices with some kind of ordering. Now that could be alphabetical ordering, A, B, C, D, E, and so on. It could be a numerical ordering if we wanted to use numbers, 1, 2, 3, 4, 5, 6, something where we can arrange those things in a particular order. Then what we can do is write down all the possible increasing sequences of those 3 letters, because the 3 letters are corresponding to our triangles, and from there we can go back and compare in our geometric figure to find all of the possible triangles in our figure. So let's suppose that somebody gives us a geometric figure that looks like this. If we go through and label all the vertices, so we've got A, B, C, D, E for the vertices around the outside, and then for the 2 points on the inside, we've got F and G. And so our goal is to count how many triangles we actually have in this figure. Well, if we begin by saying, well, let's start with the smallest vertex that we have, and that smallest vertex is A. And then if we write down all of the possible sequences that we can have, we can say that, all right, so our smallest vertex is B. What's our next smallest vertex? Well, our smallest vertex is A. Our next smallest vertex is going to be B. And then from there, we'll write down all the possibilities for the largest vertex that we can have. So ABC, ABD, ABE, ABF, and ABG. Then we go to the next smallest vertex that we can have for our second vertex. So we have ACD, ACE, ACF, and ACG. Then for the next one, ADE, ADF, and ADG. Finally, for the next smallest, AEF, AEG. And finally, for the last one, AF and G. Now, one thing that you kind of notice is that in writing these down, we end up making kind of a triangle shape. So for the number of vertices that we start, for the next column, we're losing 1 vertex. We've got 1 less of those possibilities. For the next one, 1 less than the previous one that we had there, 1 less from the previous one that we had there. And so this is one thing that we kind of discover, a pattern that we discover in writing down our vertices, that these are going to all make triangles as we're writing down all of our increasing sequences. So that's kind of an interesting observation and something that we might be able to explore a little bit later on in other counting problems. So now that we've written down all of the sequences that start with A, we can go back to our figure and say, well, which ones of those actually correspond to triangles? Well, kind of going through and just checking each one. So can we make a triangle out of vertices ABC? Yes, we can. Can we try to make a triangle out of vertices ABD? Well, no, we can go from A to B, but we can't, and we can go from B to D, but we can't go back from D with a straight line back to A. So that one doesn't count. And so if we just go through for each one of those possibilities and check to see if there's a triangle, one thing that we find is that we've got a total of 5 possible triangles where the smallest vertex is going to be A in this particular figure. Then we do the same thing for all of the triangles starting at B. So we've got BCD, BCE, BCF, BCG. Then we'll have one less number of those when our second vertex is D. BDE, BDF, BDG. Then BEF, BEG, and finally BFG. Again, we've got this triangle pattern that's showing up. Then if we go through for each one of those and check, do we actually have a triangle in our geometric figure? Well, we see that we get rid of BCE, BDF, BDG, BEF, and BEG. So from there, we'll say, all right, what's our next smallest vertex? Well, what if our next smallest vertex is C? How many possibilities do we have? Well, CDE, CDF, CDG, CFG, CEG, and CFG. And so from there, which ones actually correspond to triangles? The only one that does is CDG. Well, going over one more time, what's our next smallest vertex? Well, we've done ABC, so now next smallest vertex is D. So DEF, DEG, and DFG. None of those actually give us a triangle in our figure. And so the last one that we can have, the smallest vertex that we can have, or the largest vertex that we can have for a triangle is just going to be E, F, and G. So if we go back, we check, do we have a triangle at E, F, G? Well, we've got a line from E to F, F to G, but nothing back to E. So we can't have a triangle E, F, G. So how many triangles do we actually have in this figure? Well, if we add up all of the ones that we've counted, we see that we've got ABC, ABE, ABF, ABG, AEF, BCD, BCF, BCG, BDE, BFG, and CDG, only giving us a total of 11 triangles in this particular figure. And so we can kind of see that this particular question is maybe can be a harder question to figure out than what may just appear on the surface, in that how many triangles are actually contained in some arbitrary geometric figure that somebody can just walk up to us and hand us on the street. And so kind of the last figure that we will look at, suppose somebody gives us a 5-pointed star, and inside this 5-pointed star we've got vertices A, B, C, D, E, F, G, H, I, and J as far as those connections. And the same question as before, how many triangles are going to be contained in this figure? Well, this one is, yeah, our number of vertices is a lot bigger, and so we've got a whole lot more possibilities to try. But now that we've got a way of being systematic in counting those things, it may take us a little while to do it, but we can be confident that we can get all of them. So kind of doing the same thing as before, let's start with the smallest vertex that we can have, and that's vertex A. So from that vertex A, let's write down all of our sequences that we can have of length 3 with up to A up to J. And so if we do that, ABC, ABD, ABE, ABF, ABG, ABH, ABI, ABJ, and so on and so on and so on. Next one, we've got one less. Next column, one less. We still have our triangular structure that's in our counting, so that we know that, yes, we're doing it right. We're still getting all of our possibilities. And if we write down all of those, we see that we only have 3 triangles where the smallest vertex is actually going to be A. We do the same thing where our smallest vertex is B, and we're systematic: BCD, BCE, BCF, BCG, BCH, BCI, and BCJ for our first column. Then we're decreasing one row in each column as we move over, and so we've got a total of 28 of those possibilities, and of those 28 possibilities, only 2 of them will have triangles where the smallest vertex is going to be B. Keeping that going, if we have the smallest ones where the smallest vertex is going to be C, CDE, CDF, CDG, CDH, CDI, and CDJ, for those, we list all of those possibilities. Again, kind of going back to our geometric figure, how many of those possibilities actually correspond to a triangle in our geometric figure? Well, again, we only have 2 of those possibilities showing up. For our triangles, where our smallest vertex is going to be D, we start off with DEF, DEG, DEH, DEI, and DEJ, listing all of our possibilities from there. Then we go back to our geometric figure and say, do each one of those sequences give us a triangle? Well, there's only one triangle that has the smallest vertex of D. If we do the same thing for E, we've got our EFG, EFH, EFI, EFJs, and so on. So for that one, all of the possibilities with the smallest vertex E, no triangles work in our geometric figure. For our possibilities with the smallest vertex being F, FGH, FGI, FGJ, and so we've got 3, 5, 6 possibilities for those. Only one triangle is going to come that has the smallest vertex being F. For the 3 possibilities for triangles with the smallest vertex G, none of those turn out to work. And then finally, our smallest vertex in our triangle being H, there's only one possibility, HIJ, and sure enough, in fact, the HIJ actually does work as a triangle, so we've got that one possibility from there. So kind of putting all of these together for this 5-pointed star with vertices A, B, C, D, E, F, G, H, I, and J with those lines. How many total triangles do we have? Only 10 possibilities for triangles. ABJ, ADG, AEH, BCD, BEI, CFI, CGJ, DEF, FGH, and HIJ. Those are our only possibilities for our triangles. And so kind of what this illustrates is this notion of we can kind of have an algorithm. We can have a set of procedures, a set of steps that we can follow that will allow us to solve our problem to find out how many triangles that we have, and we do that by labeling all of the vertices in some particular order, maybe alphabetic or maybe numerical. Then we write down all of the possible sequences of increasing order, so increasing alphabetical order, and then from all of those possibilities we go back to our geometric figure to see if any of those sequences actually do correspond to one of our triangles in our figure. And in that way, we can be systematic, we can get all of our possibilities, and we can do it for any particular geometric figure that somebody could hand us. It may take us a long time to do it, depending on how many points are there, but we've got a way of actually going through and solving that problem. So hopefully this has been kind of an interesting look at maybe what turns out to be a non-trivial counting problem. So something that we can't do just really easily, really quickly. So this is kind of an example of sometimes counting does end up being hard. Hope you enjoyed it, and I will see you guys next time.